Hi everyone, Mr. Glover here. Just about to start our next set of notes. So last class we talked about how to calculate probabilities, and the big idea is that a probability of an event happening is going to be equal to the number of desirable outcomes divided by the total number of outcomes. So we're going to take this a step further today, and that we're going to actually have to calculate the desirable outcomes, and we're going to have to calculate the total outcomes. They won't be given to us in the question. And we're going to be using combinatorics from last chapter to do it. So when we know that the probability of a particular outcome is the ratio of desired outcomes to total outcomes, what if we aren't given the number of outcomes in the first place? We may need to use combinatorics to determine the total number of outcomes. Kansas, Brooke, and Chastity are competing in a race with 7 other students. All 10 students have the same chance of winning the race. Part A, determine the number of ways that Kansas, Brooke, and Chastity could place in the top 3. So we've got 3 people, Kansas, Brooke, and Chastity, and we've got 3 spots. We've got first, second, and third. If we don't really need one of them to be first, if any of the 3 could be first, second, or third, as long as the 3 of them are in it, well then 3 choices for number 1, 2 choices for number 2, and 1 choice for number 3. That gives us 6 ways that those 3 people could be picked. Or if you wanted to, you could calculate this with permutations as 3 permutation 3, where 3 people were picking 3. It's going to still give us 6. So now that we know the number of favorable outcomes, we need to know the total number of outcomes. How many ways could anyone fill those spots? So again, we've got 3 choices, first, second, and third. And this time we can fill in any student for first place. We've got 10 people to pick from. So there's 10 options for first place, 9 options for second place, 8 options for third place, which means we're going to have 720 possible ways. Or, again, we could have used 10 permutation 3 and we would still get 720 possible ways. So now that we've calculated the total outcomes and the desirable outcomes, we just have to calculate the probability that Kansas, Brooke, and Chastity place in the top 3. The probability of Kansas, Brooke, and Chastity is going to be given by the number of desirable outcomes, which is 6, divided by the total number of outcomes, which is 720. And we will have a 0.0083 probability. In terms of a percent, times 100%, we have 0.83%. So assuming that everybody is equally favored and there's no ringers and nobody's better at running than anyone else, the chances of getting all 3 of these people in the top 3 is less than 1%. There's a good chance we'll see 1 of them or maybe 2 of them, but all 3 is not as likely. What if we used combinations instead of permutations? So what if the order that they placed in didn't matter so long as they got picked? In this case, the number of desirable outcomes would simply be 3 choose 3. We've got 3 people, we're choosing 3 of them, and we're going to have 1 way to choose 3 people from 3. The number of total outcomes is going to be 10 choose 3, which would be 120. So if we do the same probability, P equals 1 over 120, we actually end up getting the same percent, 0.0083 or 0.83%. So in this case, it doesn't actually matter whether the permutations or combinations are used, get the same percentage. Let's try another one of these questions. So John meets his friend Steve at the mall for the first time in 15 years. Steve has 2 daughters with him and says that he has 3 other children at home. What is the probability that at least one of Steve's other children is a boy? So now with this question, there's a few pieces of info in here that are kind of hidden. Actually, I don't need to underline 15, so that's not really important. The fact that he has 2 daughters is important. And the fact that he has 3 other children is important. What is the probability that at least one, this is the key right here, at least one of Steve's other children is a boy? If it said 1, then we would be calculating number of ways for 1 to be a boy. But since it says at least 1, we have to include the possibilities that we have 1 boy, 2 boys, and 3 boys, because each of those could satisfy at least 1. We're going to have to add all of these outcomes together. So if he has 3 kids at home, n is going to be 3. And so if he has 1 boy and 3 children, the number of ways that that could happen would be 3 choose 1. If he has 2 boys, there would be 3 choose 2 ways for that to happen. And if he has 3 boys, 3 choose 3 would be the number of ways for that to happen. We can go and calculate these now. 3 choose 1 is 3. 3 choose 2 is 3. And 3 choose 3 is 1. So in this case, there are 7 ways to have at least 1 boy. If it was, what's the probability that he has 1 boy, there would only be 3 ways for that to happen. Could be the first child, the second child, or the third child. But because of the at least, it changes the problem. The total number of outcomes, and we're kind of running out of space here. Let's just divide this a little bit. Total outcomes are going to be first, second, and third child. Could have a boy or a girl, so 2 options. Boy or a girl, so 2 options. Boy or a girl, so 2 options. And there would be 8 possible ways to have those 3 kids. So if we want the probability that at least 1 is a boy, we just need to take the favorable 7 outcomes and divide them by the total 8 outcomes. The probability of at least 1 boy is 7/8, which means there's an 87.5% chance. And now this question is kind of tricky. I want to kind of explain a couple things here. First of all, the at least is really what makes this question, because we have to split it into cases. Second of all, interpreting the actual answer at the end. 87.5% is very likely. But this isn't saying he's very likely to have all 3 boys. It's just meaning it's very unlikely that all 3 were girls. It doesn't really, you can't really extend this into any situation other than the fact that he would have at least 1 boy. If we wanted at least 2 boys, you'd have to just take 3 and divide by 8. 3 boys would be 1/8. So these individual scenarios aren't that likely, but because we're adding all 3 together, it is very likely that one of them is true. Okay, a radio host at the Bear holds a contest at the mall. He spells out the word Saskatchewan with Scrabble letters, then places all the letters upside down and scrambles them. The contestant rearranges the letters and flips them right side up. If the rearranged letters spell Saskatchewan, then the contestant will win a new car. What is the probability of winning a new car? Okay, so let's break down the word Saskatchewan. The word itself has 12 letters, but we have to think about the repeated letters. We've got 1, 2 S's. We've got 1, 2, 3 A's. So we have to take those into account when we calculate our probabilities. N1 is 2 for the repeated A or S's, N2 is 3 for the repeated A's. Okay, so the total permutations of Saskatchewan are going to be 12 factorial over 2 factorial times 3 factorial. This is from permutations with repeated elements. There's a lot of ways to spell or to rearrange these letters. There are 39,916,800 words. So this word can become many, many, many words. The number of ways to spell Saskatchewan, total number of ways to spell Saskatchewan. Well, there's one way. You could list out every blank and write a 1 for every single letter, but there's only one way to do it. So there's only one way. So if we want the probability that we're going to get Saskatchewan, probability of Saskatchewan, number of ways to spell it is 1 over the total number of words, which is 39,916,800. The probability is super low, 2.5 times 10 to the minus 8, which is 2.5 times 10 to the minus 6%. So I don't think you should go to the mall expecting you're going to win a car. I think the people giving out the car knew that it's extraordinarily unlikely that it's going to happen. All right, let's do a couple more problems, and these will have to do with cards. So this is back with the combinations chapter from last chapter. What is the probability of drawing a 5-card hand containing 3 hearts? So favorable outcomes we'll do over here. This is going to be 3 hearts. So 3 hearts and 2 other. There's 13 of every suit in a deck. And if 3 hearts are what we want, there's 13, choose 3 ways to pick those 3 hearts. 2 others, there's 39 other cards. So 39, choose 2 are the number of ways to pick the 2 others. This works out to 286 times 741, which means there are 211,926 possibilities. Possible hands. Okay, now we have to then go and break down the total hands. In a deck of cards, we've got 52 cards, so 52. Choose 5 cards. And we are going to end up with 2,598,960 possible hands. So if we want to figure out the probability of getting our desirable hand, we have to take the number of options that match it and divide by total number of options. So probability of 3 hearts, that's going to equal 211,926 divided by the total 2,598,960. That's going to work out to 0.082, which is a probability of 8.2%. What's the probability of getting a hand with 5 spades? Actually, before we start this one, I want to kind of give you a bit of advice here. If this question had said at least 3 hearts, the favorable outcomes would have included 3 hearts, plus 4 hearts, plus 5 hearts, very much like we did up here. So be really, really careful reading the question up. Okay, what is the probability of getting a hand with 5 spades? Well, the total number of hands with 5 spades are going to be 13, choose 5. There's 13 to pick from, and we're choosing 5 of them. So it's going to be 1,287 possible hands. The total number of hands total We actually calculated already. It's 52 choose 5, and we did it above. It's 2,598,960. So if we want the probability of getting 5 spades, that's going to be 1287 divided by total number of hands, 2,598,960, which is 4.95 times 10 to the minus 4. We multiply by 100%, it's 0.0495%. So less than a tenth of a percent. It's about a 20th of a percent. So it tells you that the chances of getting a 5 cards flush with that specific suit are not particularly good. And so that's where we're going to end the notes here. This is going to take a bit of practice. This is a section that, in theory, is very simple. You just calculate the desirable outcomes, divide them by the total outcomes. However, in practice, it's not that easy, because you have to take your time setting the question up, and you need to use combinatorics to calculate these things. And we saw already last chapter that this can get pretty complicated. So it's going to be something that you need to try yourself, and you need to practice yourself, so that when you see a question about cards, you immediately know how to do it. Or when you see a question about scrambling letters with repeated letters, you remember how to do it. So I've got a few questions for you to try, but out of the textbook this time, I find that the textbook is better for this section. The workbook is kind of weird. I want you to try questions 1 to 5 in page 321. We're probably going to spend a bit of extra time on this section, but for now, this is where I'd like you to get started. So I'm going to end the chat, or end the notes. Have a great rest of your day, everyone, and I will see you all tomorrow in our Zoom chat. Bye for now.